SIEM SASE API integration. As organizations adopt secure access service edge architectures, integrating security information and event management tools with SASE components through API-based monitoring has become crucial for comprehensive security visibility and threat detection in cloud-native environments. Hit the like button, subscribe, and share. Do all the stuff that helps this channel. Thanks. API-driven SIEM integration is a game changer in the SASE framework, offering unparalleled visibility and control over security events across distributed networks. By harnessing the power of APIs, this approach seamlessly connects SIEM tools with SASE components, paving the way for more efficient and effective security monitoring and threat detection. One of the standout advantages of API-driven SIEM integration is its ability to provide centralized and normalized security event data from multiple sources within the SASE environment. This data consolidation empowers security teams with a comprehensive view of potential threats and anomalies across the entire network infrastructure. Integrating SIEM with the SASE stack offers several benefits over traditional endpoint security models. Improved threat containment. By integrating SIEM capabilities directly into the SASE framework, organizations can detect and contain threats at the web proxy level, preventing them from reaching endpoints. Enhanced scalability. API-driven integration allows more efficient data collection and analysis, enabling organizations to handle the increasing volume of security events generated in cloud-native environments. Real-time monitoring is a key feature of API-driven SIEM integration. APIs facilitate continuous real-time data exchange between SASE components and SIEM tools, enabling faster detection and response to security incidents. Customizable data extraction GraphQL support in some SASE platforms allows efficient and tailored data extraction, enabling security teams to focus on the most relevant information for their specific needs. Adopting API-driven SIEM integration in SASE architectures also aligns with the trend toward cloud-native security solutions. This approach enables organizations to leverage advanced analytics and machine learning capabilities to more effectively identify complex attack patterns and emerging threats. Furthermore, the API-driven SIEM integration supports implementing a zero-trust security model within the SASE framework, providing granular visibility to user and device activities across the network enables more accurate risk assessments and policy enforcement. As organizations embrace multi-cloud environments, API-driven SIEM integration has become increasingly crucial. It allows for consistent security monitoring and management across diverse cloud platforms, simplifying the complexities of securing distributed infrastructures. While proprietary SIEM solutions are standard in enterprise environments, open source SIEM tools are gaining traction. These tools can be integrated into SASE architectures through APIs, offering cost-effective alternatives for organizations seeking to enhance their security posture. In conclusion, API-driven SIEM integration is critical to modern SASE implementation, enabling organizations to achieve more comprehensive, efficient, and adaptive security monitoring in increasingly complex and distributed network environments. Real-time API event correlation is a critical component of modern cybersecurity strategies, particularly in secure access service edge environments. This approach leverages advanced analytics and machine learning algorithms to identify real-time patterns and relationships between API events, thereby enabling rapid threat detection and response. Event correlation in API security involves connecting seemingly disparate events to uncover potential security threats and system anomalies. And for instance, a single failed login attempt may not raise concerns. However, when correlated with multiple failed attempts across different accounts or IP addresses, it could indicate an ongoing attack. This technique is particularly valuable in SASE architectures, where API interactions are central to network operations and security. Integrating real-time API event correlation within the SASE frameworks offers several key advantages. Proactive threat detection. By analyzing patterns in API usage and correlating events across multiple sources, security teams can identify potential threats before they escalate to significant incidents. Advanced correlation techniques, such as those used in real-time API event correlation, help consolidate related alerts into single incidents, minimizing the number of notifications and allowing IT teams to focus on critical issues. This relief from alert fatigue can make IT teams feel more focused and less overwhelmed. Faster incident resolution. With more precise insights into related events and root causes, security teams can quickly resolve incidents, reducing the mean time to resolution. Enhanced anomaly detection. Automatic baselining of API behavior enables a more accurate distinction between regular activity and true anomalies, thereby reducing false positives. To implement compelling real-time API event correlation, organizations can leverage tools like API Toolkit, which offers comprehensive API monitoring and analysis capabilities. These tools can be integrated with the existing SIEM systems to provide a holistic view of the security landscape. When implementing a real-time API event correlation, it is crucial to consider various correlation techniques. Rule-based correlation, a method that relies on predefined rules to link events, provides a sense of control to security teams. For instance, correlating a spike in server CPU usage with network latency events can help identify potential threats, making security teams feel more confident in their ability to respond effectively. Time-based correlation. This technique groups events within specific timeframes to identify sequences that may indicate security issues. Machine learning-driven correlation. Advanced algorithms can identify complex patterns and relationships that may not be apparent through rule or time-based methods. By employing these correlation techniques, organizations can gain deeper insights into their API security posture and respond more effectively to potential threats. This approach aligns well with the SASE model, which emphasizes the importance of continuous monitoring and adaptive security measures in native cloud environments. As API-driven architectures have become increasingly prevalent, the ability to perform real-time event correlation across diverse API endpoints is crucial for maintaining robust security in SASE implementations. This capability enables organizations to detect and mitigate sophisticated attacks that may exploit multiple vulnerabilities across different parts of the network infrastructure. The Secure Access Service Edge and API security monitoring form a powerful combination of modern cybersecurity strategies, offering comprehensive protection for distributed networks and cloud-based applications. This integration is crucial as organizations increasingly rely on APIs for inter-service communication and data exchange. SASE provides a unified approach to network security by combining wide area network capabilities with cloud-native security functions. This framework's API security monitoring protects the critical interfaces that connect various services and applications. Organizations can achieve more granular control over data access and movement across networks by incorporating API security into the SASE model. A key aspect of SASE and API security monitoring is the implementation of continuous monitoring and auditing of API activities. This ongoing surveillance helps to detect potential security incidents quickly, allowing for a rapid response to emerging threats. Advanced SASE solutions can be integrated with API management systems to provide real-time visibility of API usage patterns, anomalies, and potential vulnerabilities. To enhance API security within a SASE environment, organizations should consider implementing the following measures: strong authentication and authorization mechanisms to restrict API access to authorized users and applications only. Encryption and data masking techniques to protect sensitive information transmitted through APIs. Regular security assessments and penetration testing of APIs to identify and address vulnerabilities. Implementation of rate limiting and throttling to prevent API abuse and potential denial of service attacks. The SASE platforms often provide built-in capabilities for API monitoring and protection. For instance, some solutions offer aggregated monitoring APIs that allow organizations to query information about applications, threats, URLs, and licenses across all tenants. This centralized approach simplifies security management and provides a holistic view of an organization's API landscape. Moreover, integrating SASE with security information and event management systems can further enhance API security monitoring. SIEM solutions can aggregate and analyze log data from across the network, including API-related events, to detect threat scenarios and correlate security incidents. This integration enables more sophisticated threat detection and response capabilities, leveraging the strengths of both SASE and SIEM technologies. As organizations continue to adopt cloud-native architectures and microservices, the importance of robust API security monitoring within SASE frameworks will increase. By embracing integrated security approaches, businesses can better protect their digital assets, maintain compliance with regulatory requirements, and ensure the integrity of their data and applications in an increasingly interconnected world. Automating threat detection workflows is critical to modern cybersecurity strategies, particularly in Secure Access Service Edge, or SASE environments. By leveraging artificial intelligence and machine learning algorithms, organizations can significantly enhance their ability to identify and respond to security threats in real time. One key benefit of automating threat detection workflows is the ability to process large amounts of data quickly and accurately. AI-driven security tools can analyze network traffic patterns, user behavior, and system logs to identify anomalies that may indicate potential threats. This automated analysis helps security teams overcome the challenge of alert fatigue, a common issue in traditional security operation centers. Machine learning models can be trained to recognize complex attack patterns and evolving threats, enabling more sophisticated detection capabilities. For example, these models can identify subtle indicators of compromise that rule-based systems, such as unusual API call sequences or unexpected data access patterns, may miss. Automated threat detection workflows often incorporate intelligence feeds to remain current with the latest known threats and attack vectors. This integration allows security systems to automatically update their detection rules and algorithms, ensuring they remain effective against emerging threats. In SASE architectures, automated threat detection can be applied to various security functions. Network security involves analyzing traffic patterns to detect potential DDoS attacks or network intrusions. Cloud access security brokers, or KASBs, monitor cloud application usage for signs of data exfiltration or unauthorized access. Secure web gateways, or SWGs, identify and block malicious URLs or web-based threats in real time. Zero Trust Network Access, or ZTNA, continuously verifies user and device trustworthiness based on behavior analysis. Automation also plays a crucial role in orchestrating security responses. When a threat is detected, automated workflows can initiate predefined response actions such as isolating affected systems, revoking user access, or updating firewall rules. This rapid response capability is essential for minimizing the potential impact of security incidents. Organizations should consider the following best practices to implement effective automated threat detection workflows. Establish explicit baseline behaviors for users, devices, and applications to identify deviations accurately. Implement a centralized logging and event correlation system to provide context for automated analysis. Machine learning models should be regularly updated and fine-tuned to improve detection accuracy and reduce false positives. Integrating automated threat detection with human-led threat hunting and incident response processes is necessary for a comprehensive security approach. As the threat landscape evolves, automated threat detection workflows will become increasingly sophisticated. Future developments may include more advanced AI capabilities such as natural language processing for analyzing unstructured data sources and predictive analytics to anticipate potential security risks before they materialize. By embracing automated threat detection workflows within their SASE frameworks, organizations can significantly enhance their security posture, reduce response times, and more effectively protect their digital assets against a wide range of cyber threats. Cross-platform API compatibility ensures seamless integration and functionality across diverse operating systems, devices, and programming environments in the context of Secure Access Service Edge, or SASE, and API security monitoring. This approach enables organizations to develop and maintain consistent security measures across their network infrastructure, regardless of the platform used. Cross-platform API compatibility is essential in SASE environments for several reasons. Unified security policies. This allows for consistent security policies across all platforms, ensuring that the same level of protection is applied to access resources from a Windows PC, Mac OS device, or mobile platform. Seamless user experience. By providing a standardized interface, cross-platform APIs enable a uniform user experience across different devices, which is crucial for maintaining security without compromising usability. Efficient development. Cross-platform APIs reduce the need for platform-specific code, allowing developers to create security solutions that work across multiple environments with minimal modifications. Key principles must be followed to achieve cross-platform API compatibility in SASE implementations. Consistency in design. APIs should maintain a standardized interface and response structure across all supported platforms. This includes consistent endpoint structures, naming conventions, and error handling mechanisms. Flexibility and adaptability. APIs must be designed to accommodate evolving requirements as platforms change. Modularizing API components and creating endpoints that handle various inputs and outputs allows updates without breaking the existing implementations. Performance optimization. APIs should be optimized to work efficiently across devices with varying processing capacities, from IoT devices with constrained hardware to high-performance web applications. Protocol support. Implementing support for widely used protocols such as REST, GraphQL, and WebSockets ensures compatibility with various platforms and programming languages. Data format standardization. Using universally supported data formats such as JSON for API responses promotes interoperability across different systems. SASE providers often leverage cross-platform development tools and frameworks to enhance cross-platform compatibility. For instance, using technologies such as React Native or Flutter for mobile app development allows for code sharing between iOS and Android platforms, thereby reducing the likelihood of platform-specific security vulnerabilities. Testing plays a critical role in ensuring the cross-platform API compatibility. Implementing rigorous testing procedures across various browsers, devices, and operating systems using tools such as Selenium or BrowserStack helps to identify and resolve compatibility issues before deployment. By prioritizing cross-platform API compatibility, organizations can create more robust and flexible SASE solutions that adapt to the diverse and evolving technology landscape. This approach enhances security consistency, operational efficiency, and user satisfaction across the entire network infrastructure. Real-time anomaly detection systems are critical components of modern cybersecurity frameworks, particularly in Secure Access Service Edge or SASE environments. These systems continuously analyze network traffic, user behavior, and system logs to identify unusual patterns or activities that may indicate potential security threats. At the core of real-time anomaly detection, advanced algorithms process vast amounts of data to establish baselines for expected behavior. Machine learning models such as isolation forests and local outlier factors, or LOF, are commonly employed to detect anomalies in high-dimensional data sets. These techniques are particularly effective for identifying fraudulent activities in financial systems and unusual access patterns in network logs. In SASE architectures, real-time anomaly detection systems leverage a network's distributed nature to provide comprehensive security coverage. They monitor data flows across various SASE components, including secure web gateways, cloud access security brokers, and zero trust network access points. This holistic approach enables the detection of sophisticated threats, that can exploit multiple vulnerabilities, across different parts of the infrastructure. A key advantage of real-time anomaly detection is its ability to identify unknown or emerging threats that signature-based detection methods might miss. By focusing on behavioral anomalies rather than known attack patterns, these systems can uncover advanced persistent threats, or APTs, and insider threats that often evade traditional security measures. Many organizations integrate real-time anomaly detection systems with security information and event management, or SIEM, tools to enhance their effectiveness. This integration allows for the correlation of anomalies detected across different network segments, providing a more comprehensive view of potential security incidents. For instance, an unusual login attempt detected by the anomaly detection system can be correlated with other suspicious activities logged by the SIEM, enabling a faster and more accurate threat assessment. Real-time anomaly detection systems often employ a combination of statistical methods and AI-powered analytics to achieve high accuracy and low false positive rates. Techniques such as Z-score analysis and interquartile range, or IQR, are used alongside machine learning models to provide a multi-layered approach for anomaly detection. This hybrid approach helps distinguish between genuine security threats and benign anomalies, reducing alert fatigue for security teams. Implementing real-time anomaly detection systems requires careful consideration of the data pre-processing techniques. Variational mode decomposition, or VMD, is a technique used to extract periodic components from time series data, allowing faster and more accurate anomaly detection in telemetry systems. This approach is beneficial in environments where rapid detection is crucial for minimizing potential cyber attack damage. As organizations continue to adopt cloud-native architectures and microservices, the importance of real-time anomaly detection within SASE frameworks will increase. These systems provide the agility and scalability required to protect dynamic, distributed networks against an ever-evolving threat landscape. By leveraging advanced analytics and machine learning, real-time anomaly detection systems enable organizations to maintain a proactive security posture and identify and mitigate threats before they can cause significant harm to network or data assets. Zero Trust API security models represent a paradigm shift in how organizations approach API protection, aligning with the broader Zero Trust security framework. This model operates on the fundamental premise of never trust, always verify, to ensure the utmost security in the digital realm. In the context of APIs, this means treating every API request as potentially malicious, regardless of its origin or previous interactions. The core principles of Zero Trust API security models include the following: continuous authentication and authorization. Every API call is authenticated and authorized in real time using token-based authentication, such as OAuth, multi-factor authentication, and risk-based adaptive authentication. This ensures that even if the credentials are compromised, the attacker's ability to misuse them is limited. Least privilege access. API access is granted based on the principle of least privilege, where users and systems are given only the minimum level of access necessary to perform their functions. This minimizes the potential damage if a breach occurs. Micro-segmentation, APIs are divided into smaller, isolated segments, each with its security perimeter. This approach contains potential breaches and prevents lateral movement within the API ecosystem. Continuous monitoring and analytics. Real-time monitoring of API traffic and user behavior helps quickly detect anomalies and potential threats. Advanced analytics and machine learning algorithms can identify complex attack patterns that may evade traditional security measures. Data-centric security, Data protection is paramount in zero trust API models. This includes end-to-end data encryption in transit, at rest, and data validation and sanitization for every API request. Device trust, the security posture of devices that make API calls, is continuously assessed. This might include checking for up-to-date security patches, antiviral software, or device fingerprinting. Implementing a zero trust API security model requires a multi-layered approach. API gateways. These are critical components in enforcing zero trust principles, providing capabilities such as authentication, rate limiting, and traffic monitoring, identity and access management, or IAM. Robust IAM systems are essential for managing user identities and permissions across the API ecosystem. Encryption. Strong encryption protocols such as TLS 1.3 should be used for all API communications, API discovery and inventory. Organizations must maintain a comprehensive inventory of all APIs, including shadow or undocumented APIs, to ensure complete coverage of the security model. Continuous validation. Even after the initial authentication, each API transaction should be scrutinized for potential security risks. While zero trust API security models offer significant benefits, they also present challenges. These include increased implementation complexity, potential performance impacts due to continuous verification, and the need for cultural shifts within organizations to embrace the never trust mindset. As APIs continue to play a central role in modern application architectures, adopting zero trust principles is crucial for protecting sensitive data and maintaining the integrity of digital systems. This approach provides robust defense against sophisticated cyber threats in an increasingly complex and distributed IT landscape. The future of Secure Access Service Edge, or SASE, in an API security is poised for significant advancements driven by emerging technologies and evolving threat landscapes. Several key trends are shaping the trajectory of these interconnected domains. Artificial intelligence and machine learning integration, AI and ML, play an increasingly crucial role in SASE and API security. Advanced algorithms enable more sophisticated threat detection, anomaly identification, and automated response mechanisms. These technologies will help organizations stay ahead of evolving threats by predicting potential vulnerabilities and adapting real-time security measures. Edge computing and SASE convergence. As edge computing grows, SASE solutions must adapt to provide security and connectivity at the edge. This convergence reduces latency, improves performance for real-time applications, and enhances the security of IoT devices and distributed networks. Zero trust architecture adoption. Zero trust principles will become more deeply integrated into SASE and API security frameworks. This approach ensures that every access request is authenticated, authorized, and encrypted, regardless of origin or destination, thereby providing a more robust defense against sophisticated attacks. API-first security strategies. As APIs become increasingly central to business operations, organizations are adopting API-first security strategies. These strategies involve implementing advanced authentication mechanisms, threat detection tools specifically designed for APIs, and continuous monitoring of API traffic patterns. Quantum-resistant cryptography. With the looming threat of quantum computing potentially breaking current encryption methods, SASE and API security solutions will begin incorporating quantum-resistant cryptographic algorithms to future-proof data protection. Automated API discovery and classification. As the number of APIs within organizations continues to grow, automated tools for API discovery, categorization, and monitoring become essential. These tools will help organizations maintain an accurate inventory of their APIs and ensure comprehensive security coverage. Integration of SASE with 5G networks. The rollout of 5G networks will necessitate integrating SASE solutions to provide secure and high-performance network services at scale. This integration will enable organizations to leverage the increased speed and connectivity of 5G while maintaining robust security measures. Enhanced data protection and privacy controls. With evolving privacy regulations, SASE and API security solutions will incorporate more advanced data protection features, including enhanced encryption techniques and granular privacy controls. By embracing these trends, organizations can enhance their security posture, improve operational efficiency, and better protect their digital assets in an increasingly complex and interconnected technological landscape. Thanks for watching, and remember, be nice to geeks.